Okay, so what we had done in the last week was we claimed that what we will be eventually interested in will be matrix elements of this form. Phi eval acting at some point, so we create a particle. This is a state which contains a particle at x0, and then we let this state evolve, and we would like to, for example, ask if what is the amplitude to have a particle at the point x1 at a later time. So we said that this was basically, we start with the state x0, we evolve it, and this is the matrix element we would like to calculate. And then after doing lots of algebra, we had seen that this matrix element is actually given by we are in the full theory, we are creating a particle from the vacuum of the full theory, not necessarily the empty state, that is the minimum energy state. And then we said that this matrix element that we are interested in is actually this one, time ordered product of phi plus x1, phi plus x0, e to power minus I v of t dt from minus infinity to infinity divided by this one. And this 0 over here, okay, so this omega is the ground state of the full theory, whereas 0 is the ground state of the free theory. Which is essentially the zero particle state. Now we could also as well ask a similar question. Let's say that we have two particles in the initial state, particle A at the point x0, and even we can have different particles, particle B at the point x1, and we can ask what is the amplitude to have a particle C at the point x2 and particle D at the point x3 at a later time. T final minus T initial. And still, well, just you can repeat the same derivation. This will also turn out to be just the same matrix element. Time ordered product, phi C. Sorry, here this is not dagger. Phi C at x2, phi D at x3, phi A x0 dagger, phi B x1 dagger, e to the power minus I v t dt from minus infinity to infinity divided by 0, the time ordered product without the inner fields, just the exponent. And keep in mind that in these matrix elements, on the right-hand side, everything is in the interaction picture. That is where the time dependence of the operators comes from. The potential is also in the interaction picture. And okay, here I also said that Vt dt from minus infinity to infinity is actually V of phi d4x. Because the potential Vt, what we call Vt, is just the three-dimensional integral of the potential in terms of the fields. And yes, that's extra. And then we said, okay, as an example, let's just take V of phi as a lambda over 4 factorial, phi to the 4. Then looking at the two-point correlation function, this is what's called a correlation function, phi of x1, phi, no, phi of x0, which we said could be written as a 0 time ordered product of phi of x1, phi dagger of x0, e to power minus I d4x, lambda over 4 factorial phi to the 4 divided by 0 time ordered product and we said that we can expand the exponent as a Taylor expansion, so this will be 0 time ordered product phi of x1 phi plus of x0. Let me put only the connected parts, because the disconnected parts we argued that they are cancelled by the denominator, plus phi of x1 phi plus of x0 d4y minus I lambda over 4 factorial phi to the 4 of y plus we essentially have an infinite sum d4y1 d4y2 minus I lambda over 4 factorial squared phi to the 4 y1 phi to the 4 y2 etc. And then we said that okay, these we can interpret in terms of Feynman diagrams using Wick's theorem. What Wick's theorem told us was if you have any time ordered product of any number of operators, this is actually equal to the sum of the normal ordered product of the same operators with all possible, including 0 or more, contractions. Well, this is true for a non-interacting theory. And in fact, once we convert, you see, here we start with a fully interacting theory, a matrix element of the fully interacting theory, but on the right-hand side, we actually have a non-interacting theory. All the interactions of the left-hand side are already in V. All the other time evolution in this, on the right-hand side, is determined by H0. Not H. So that's why the right-hand side is a non-interacting theory. So for the right-hand side, we can use the Wick theorem, which is correct for the non-interacting theory. Now, what we mean by a non-interacting theory and why the Wick theorem is correct for the non-interacting theory will be more clear when we discuss, for example, the path integral formalism. Because if you remember, in deriving the Wick theorem, there was a crucial point we were using. The contractions which were just the commutators of the positive and negative frequency parts, they are not operators. This won't be true for an interacting theory. And then using this Wick theorem, what we did was, for example, this first term is just a single line connecting x0 to x1. Then the second term, by the way, here I have a 1 over 2 factorial from the exponent. Again, these are only, I will only take the connected pieces. And this is from x0. I should start from x0, go to x1, and in between there is a y. At the point y, there are 4 lines. So the connected part will be just, I connect x0 to this y, and x1 to that y, and there are these 2 free lines, I just connect them together. This is the only connected diagram. And then the corresponding expression for this one is actually, I mean, for this line, this we had already explicitly calculated. There's a single part, single contribution there. We had calculated that to be as, let's call it x1 minus x0, from x0 to x1. So here we have a line connecting x0 to y, so this is y minus x0. There is a line, this one, connecting y to x1 minus y, and there is a line connecting y to y minus y. And there is this vertex. Vertex is basically this factor over there. And we have minus I lambda. You see, in this let's look at this diagram. Typically, you have, for each vertex, you have 4 fields at each vertex. And you will be connecting each one of these 4 fields to some other field somewhere else. So here there are, in fact, 2 fields at x1 and x0. But in the general case, you might have more than 4 fields at positions other than the y. So you have a vertex at y. You have other fields at other positions, other vertices maybe, or these explicit external fields at some other points maybe. So you have these 4 lines, 4 fields. They should be contracted with any one of the other 4. But just if you consider one field contracting with one of these 4 fields, that field can actually be contracted with any 4 of them. And all of them will give me the same contribution. So there's a factor 4. And if you consider another field that will be contracted with one of these fields in the vertices, there are 3 left. So there's a factor 3. And each one of these 3 choices will give the same contribution. So rather than calculating all 3 separately, we just calculate one of them and multiply by 3. Again, there will be some other field contracted with this vertex. There are 2 options left, all of which will give the same answer. So just calculate the contraction with one of them, multiply by 2, and the 4th field is just contracted with the remaining field. So there is a factor of 4 times 3 times 2 times 1, which is actually this 4 factorial. That is why we insert the 4 factorial over there. So we have the 1 over 4 factorial from the interaction term in the Hamiltonian. But there are the 4 factorial different ways that these 4 fields can be contracted. Unless, for example, in this particular case, what happens is we have 2 other fields, except on the fields at the vertex, just 2 of them. So one of them can be contracted in 4 different ways. That's the factor 4. The other one is contracted in 3 different ways. So we have 2 fields left at the vertex. I can contract this one with this, or this one with this. They will be essentially the same thing. So we actually have, that is what we call the symmetry. So this diagram basically has a symmetry factor of 2. So that's why we have the divided by 2. That is what is written in the book. Calculate the symmetry factor of the diagram. That symmetry factor essentially corresponds to that loop. I can draw that loop like this or like this. It's the same. So that's why we have a symmetry factor of 2 for this. This 4 factorial is cancelled with 4 factorial. For each vertex, we have minus I lambda in the Feynman diagram without the 4 factorial. And then you have to divide by 2, which is called the symmetry factor. Now let's go to the other diagram, other term. In this case, we have more options. Again, I will just draw the connected diagrams. Well, the possible diagrams we have are, okay, there is the x0 that goes to y, y1, which goes to x1. At y1 we have a loop, and here we have another vertex, another loop. y2, this is one possible diagram. Or we have this diagram from x0 to y1. And then from y1 we have 3 lines that goes to y2. And then from y2 we go to x1. Yeah, of course you can exchange y1 and y2, but the graphs will look identical. So that's why I'm not drawing them. I will just multiply by the corresponding factor. Now, if you look at the propagators, if you look at the corresponding expression, well, let's say here I have a line connecting x0 to x1 that will give me a propagator y1 minus x0. Then a line connecting y1 to x1. Then I have a propagator x1 minus y1. Then I have a propagator connecting y1 to y2. And the propagator connecting y2 to y1. So this line and this line. Then I have another propagator connecting y2 to y2. Each line gives me a propagator. I just multiply the propagators. Of course, there is a y1 and y2 integral. The point y1 and y2 are not fixed. Here I have a y integral. The point y is not fixed, d for y. Here I have a d for y1, d for y2 integral. Then I have to calculate the overall factor. Well, I have 2 vertices minus I times lambda squared. Well, if you look at the exact expression over here, we have divided by 4 factorial, and then I have a factor 1 over 2. 1 over 2 factorial. Now, this 1 over 2 factorial is from the exponent. So that number 2 over here, if I look at the nth term, let's say, I will have n vertices, and there I would get n factorial. But you see, this vertex and this vertex, they are essentially identical. I can connect, I can just exchange their positions, exchange the positions of the vertices, but I will still get the same contribution. Of course, y1, y2 will be different, but the contribution will be exactly the same. So in how many ways I can rearrange n vertices? N factorial. In this case, it is 2. Just you have n vertices. If you have n vertices, you can just rearrange them in n factorial different ways. And each one of these rearrangement of the vertices will give me exactly the same result. So rather than calculating n rearrangement of the vertices, I just calculate one of them, multiply by n factorial. But that cancels this 1 over 2 factorial. So that's why, even in the nth order, just pick up one ordering of the vertices and calculate its contribution. Ignore the 1 over n factorial from the exponential. Remember, at nth order, from the exponential, you get 1 over n factorial. But then from the rearrangement of the vertices, you have n factorial identical contributions. They will just cancel. Now, again, the same reasoning goes over here as in the previous case. For each vertex, there are 4 fields. These 4 fields will be contracted by some other fields at some other positions, maybe. If there are some other fields from some other positions, I just choosing which field I contract with, I get 4 factorial, say, identical contributions. So that will cancel this 1 over 4 factorial. But then we have some problems. You see, here, if you look at these lines, You see what we did here. I contracted y1 with one extra line. There are 4 choices for this line. There are 3 choices left for this line. But for this line, at y1 I have 2 fields left. At y2 I have 4 fields left. I have 4 choices for this line. 3 times 4 2 times 4 choices. Let me just multiply, write it explicit. There are 4 choices for this contraction, 3 choices for this contraction. Now for these choices there are 2 lines at 2 fields at y1, but 4 fields at y2. So there are 2 times 4 contractions over there. And here for this line there are just 3 contractions. And for this line there are just 1 possible choice. What happened there? We have 4 times 3 times 2. I have 1 4 factorial. Then I have 4 times 3. I have almost a 4 factorial, but I'm missing a factor 2. Again, for this diagram, apparently I would have expected a symmetry factor 4, but there's 2. If I didn't make a mistake somewhere. Okay, there are 4 choices here, 3 choices here, 2 fields left. Pick up one of them, and that can go to y2 in. No, so okay. There are no factors 2 over there. You see, what happened? I contract, okay, x0 can be contracted with 4 choices at y1. x1 can be contracted with 3 remaining choices at y1. So at y1 I have 2 fields left. Pick up the first one. It can contract with any one of the 4 fields at y2. Pick up the second one. It can contract with 3 fields from y2. Well, why don't I don't have the factor 2 there because both of those fields are connected with y2. So here I have 4 times 3 times 2. No, 4 times 3 times 2 times 1. I have 1 4 factorial, but the other one is 4 factorial divided by 4. I have 3 times 2. Now, what are those 2 symmetry factors? One is that loop at the top. I had left with 2 fields. I can flip them. The other one is the exchange of these 2 lines. I can just flip those 2 lines. So that is the other symmetry factor of this graph. So for this graph, the symmetry factor is 4. Now let's look at this diagram. Can you guess the symmetry factor? Well, I can exchange any one of these 3 lines. 3 factorial. Well, let's see if it will be actually correct. So first, let's write down the propagators. I have a line connecting x0 to y1. That will be y1 minus x0. I have 3 lines connecting y2 to y1. Each one will bring such a one propagator from y1 to y2. So I have cube. Then there is a propagator from y2 to x1. And, well, from the expansion, okay, I have minus I lambda for each vertex divided 2 squared divided by 3 factorial. That is my guess. 6 is the symmetry factor, minus I lambda is the vertex factor. At each vertex, I just assign minus I lambda. Let's see if it is correct or not. I have from the expansion minus I lambda divided by 4 factorial squared. Then I don't write the 1 over 2 factorial because that is just we are exchanging y1 and y2. That is already cancelled. Now let's see. Let's look at this one. x0 connecting to y1. There are 4 choices for that. x1 connected to y2. There are 4 choices for that. Let me just pick up one of the fields left at y1. That can be connected with any one of the 3 remaining left. The second field at y1 can be connected with any of the 2 fields left. So here there is 1. So if I multiply this by, there is a 4 times 3 times 2 times 1, that is 4 factorial, times 4. 4 is 4 factorial divided by 3 factorial. Which one? How we count these possibilities? You see, what do I have? This is x0, there is a single field at x0. Here is x1, there is a single field at x1. Now here, this is y1, there are 4 fields. 1, 2, 3, 4. Here, y2, there are again 4 fields. Okay. Now this x0 can actually be connected with any one of those 4 fields. So you see, here we have 4 possibilities. I just connected to one of them and multiply the result by 4. Here, x1 should be connected with one of the fields at y2, but it can be any one of the fields. So I just connected with one of them and multiplied by 4 because every choice of those 4 fields will give me the same answer. Now let's look at this line. This line will be connected to, this field will be contracted with one of these 3 fields at y2, and each one will give me the same answer. So I contracted with one of them and multiply the result by 3. This line, this field will be contracted with one of the remaining 2 fields. Well, any contraction will give me the same answer. So I just contract with one of them and multiply by 2. And the remaining fields, they have to be contracted. So the factor is 4 times 3 times 2 times 1, which is 4 factorial, and then 4. But 4 is 4 factorial over 3 factorial. So I just wrote 4 times 3 factorial and divided by 3 factorial. So here I have a 4 factorial, here I have another 4 factorial squared. This cancels this one. So the remaining term is just 3 factorial. So my initial proposition was correct. The symmetry factor is 3 factorial. Now, any questions? Now, okay, I wrote it already. Now, okay, you can leave it like this, or if you like, you can just write it as in terms of the Fourier components, because we already had said that the propagator is just this integral, d4k e to power I kx divided by k squared minus m squared plus I epsilon divided by 2 pi to the 4. This is my propagator. Let's see. I would rather just take. No. Let us use it to calculate this diagram, this one. Or the contribution is actually this. I will be ignoring the factors. I'm just interested in the integral. Well, there are many, I have 5 propagators. So basically I have 5 integrals, 5 momentum. So let me just write d for y1, d for y2, d for ki divided by 2 pi to the 4, I from 1 to 5. And then I have 1 over ki squared minus m squared plus I epsilon for each one of the propagators. Let me write explicitly the y dependencies. I have e to power minus I k1, y1 minus, well, let me write it slightly differently. Exponent minus I k1 times y1 minus x0, minus I k2, y2 minus y1, minus I k3, y2 minus y1, minus I k4, y2 minus y1, minus I k5, x1 minus y2. Well, here, the momentum of this one, I called it k1, the momentum of this one, I called it k2, and the momentum of each one of these, no, this is k5, and momentum of each one of these 5 propagators are k2, k3, k4. I will take the y1, y2 integrals. Let me write everything that doesn't depend on x0 and that doesn't depend on yi. I have plus I k1 x0 and minus I k5 x1. Those are the only 2 terms that don't depend on yi's. You see, the y is, I can connect the, let's say, the y1 terms, and it will just give me e to power minus I y1 times some 4 vector, but y integral just gives me the Dirac delta. So I will just right away write the Dirac delta, the 4-dimensional Dirac delta. This is from the y1 integral. So this is k1 minus k2 minus k3 minus k4. Then I have the y2 integral. Similarly, the y2 integral will also give me a Dirac delta. Now k2 plus k3 plus k4 minus k5. Now I have 5 momentum integrals, 2 Dirac deltas. I can just evaluate 2 of the integrals using 2 of these Dirac deltas. Well, it's up to you to choose from. Well, diagrammatically, the diagram we are evaluating was this one. And I actually assigned the momentum k1 to here, k5 to here, k2 here, k3 here, and k4 here in a sense. So what I will do is I would rather keep k1 integral. And then I would just evaluate the k2 and k3 integrals explicitly. Yeah, that might even be better. Okay, the easiest one would be just to evaluate the k1 and k5 integrals. But I mean, since k1 and k5 are already in the exponent, I would rather keep k1 and k5. So I will evaluate k2 and k3. I would like to have a simple exponent. I don't want to write a long exponent. So let's say this is, let's evaluate K2. So we have D4 K1, D4 K3, D4 K4, D4 K5 divided by 2 pi cubed 1 over K1 squared minus m squared plus I epsilon. Well, let me write even that one, let me write it in this form. With the understanding that K2 is actually K1 minus K3 minus K4. I'm using the first Dirac delta. I'm evaluating the K2 integral. Then I would have exponent I K1 x0 minus I K5 x1. And then I have a Dirac delta for K1 minus K5. Well, I'm obliged to take one of those K integrals. I will take the K5 integral. So this just gives me d cubed d4 K1. This tells me that K1 is equal to K5. d4 K1 divided by 2 pi to the 4 e to the power I K1 x0 minus x1. Then I have d4 K3 divided by 2 pi to the 4 d4 K5 K4 divided by 2 pi to the 4. And then I have product over I from 1 to 5, 1 over Ki squared minus m squared plus I epsilon, with the understanding that K2 is equal to K1 minus K3 minus K4, and K5 is equal to K1. And that's it. And let me even change this slightly. So this is x1 minus x0 minus I. But you see what we were evaluating? We were evaluating this expression. Time-ordered product of phi dagger x0, phi of x1, which is called the Feynman propagator from x1 minus x0. And we can also define this Feynman propagator as its Fourier transform, d4k divided by 2 pi to the 4, e to the power minus I k x1 minus x0, the Feynman propagator at the momentum k, whatever that is. And this one this was the propagator of the free theory. Let's also call that SF0. And which is, again, we can just write it as a Fourier transform. Multiply by SFK of the free theory, where we had defined this SF0 of k is 1 over k squared minus m squared. By the way, I have one mistake. Here I had a minus I. In the definition of the propagator, there is a minus I. You see, remember the propagator, it looked like a real expression. We wrote it as a loop integral, using the residue theorem. But if we want to replace the path integral in terms of a loop integral, we have to have, we have these step functions. We replace the step functions with loop integrals, but then we have to divide by the 1 over 2 pi I, because the loop integrals are 2 pi I times blah, blah. One of these 2 pi's just gave us this 2 pi to the 4. One of those factors is over there, and minus I is our 1 over I. And so here I have each one of these are minus I. So then you see, what do we have? SF x1 minus x0 is actually equal to SF0 x1 minus x0 plus, we have this loop integral with the factors. And plus other terms. But you see, SF itself has this 4-dimensional integral e to power ik blah blah. SF0 has the same Fourier transform expression. This factor we calculated also has the same, exactly the same expression. So we can just take the Fourier transforms of both sides, if you like, and that would give us SF of k is actually SF0 of k plus minus I lambda squared over 3 factorial, all these factors. Now, of course, now we called K1 and K5 as K. I can even simplify it further. This is SF0 K plus minus I lambda squared over 3 factorial SF0 K, because you see here I have 1 minus I over K squared minus M squared plus I epsilon. That doesn't depend on K3 or K4. I can just take it out of the integral. Inside, what remains is D4K3, D4K4 divided by 2 pi to the 4, 2 pi to the 4. Inside I have one over, well, I have the K2, K1 is K minus K3 minus K4 squared minus M squared plus I epsilon minus I divided by K3 squared minus M squared plus I epsilon minus I, or even instead of these, SF0 K minus K3 minus K4 times SF0 K3 SF0 K4 times SF0 K. Now let's remember our diagram again, plus other terms, of course. This was the diagram. And this was K1, this was K2, this was K3, this was K4. and this was K5. Now what did the Dirac deltas tell me? Instead of K1, I just renamed it to K. Dirac delta told me that K5 should also be K. Now I have the K3 and K4 integrals left, and K2 is just K minus K3 minus K4. So let's see. Let me put the arrows. I have a particle with momentum K coming. It is dissociated into three different particles. One of the particles have momentum K3, the other one has momentum K4. And the third one hence has to have the momentum K minus K3 minus K4. So these three particles propagate and then they combine again to form a single particle whose momentum, if you use momentum conservation, just K. And how do you write the Fourier transform of this contribution to the propagator? Well, just multiply the propagators. You see we have SF0K from this line. Here I have SF0K again from the final line. In between I have a propagator with momentum K3, another one with propagator K4, another one with propagator K minus K3 minus K4. I only use momentum conservation. Now, what is the momentum K3? Is it fixed? No, there is nothing that fixes the momentum K3, neither the momentum K4. They can take any values. So what quantum mechanics tells me, if you have more than one amplitude contributing to the process, sum the amplitudes. So any value of K3 and K4 are possible, so I just sum the amplitudes. Well, K3 and K4 take continuous values, so I integrate over K3 and K4, each one with a factor 2 pi to the 4. These 2 pi to the 4s are due to my normalization. I chose not to have any factors 2 pi in x integrals, so all the 2 pi factors are in the k integrals. Am I done? Not really, because any Feynman diagram basically have propagators and vertices. So these are the contributions from the propagators themselves, but then I have also the contributions from vertices. What are they? And for this theory, for each vertex, I add a factor minus I lambda. So I have two vertices minus I lambda squared, and then divide by the symmetry factor if there are any. In this diagram, the symmetry factor is 3 factorial. So this is the contribution to the, you see here I have the free propagator plus, this is one of the corrections. And how do you calculate the corrections? Once you draw the Feynman diagram, well, this is how you write the corresponding contribution. For each line, write the corresponding propagator. For each vertex, write the corresponding vertex factor. So this is a vertex factor. And these are propagators of our theory.
Simetri faktörü hesapladığınız kısmı anladın mı? Mesela şekle baktığın zaman 3 faktöriyel direkt şeyden mi geliyor? Şu ortadaki 3 line.
Exactly. Just a rearrangement of those 3 factors. You see, why do we have those 3 factors? Let's just look at these 3 lines. If these 3 lines went to 3 different vertices, now which vertex is connected to which field? Well, I don't know. There are 3 possibilities. So just pick one and multiply by 3. Which field goes to this vertex? Well, there are 2 possibilities. Contract by 1, multiply by 2, and this similarly over here. And here there is no symmetry. But you see, if all of those go to the same vertex, well, taking this to this vertex and this, I don't have these 3, 2, 1 choices. All of them go to the same vertex anyway. So there's this factor of 3 factorial will be missing if all those 3 lines go to the same vertex. That's why it's called the symmetry factor. It's a symmetry of the graph, not a symmetry of the theory or the fundamental interaction. It's a symmetry of the mathematical graph. Well, you see, most of the time what you are interested in is you just send particles, like 3-4 particles, and then 3-4 other particles, and they collide. And you want to see what happens at the end. Or you can even send one particle and it decays into 3 particles. So you can look at diagrams, let's say, of this form. At 0th order, the contribution is 0. At first order, well, you have such a diagram. At higher orders, well, you can have more complicated diagrams, like, let's say this comes to here. One of this goes to the outer out, so we have a loop over here, and 2 lines come from here, and you have such a diagram, for example, in this case. Before, for simplicity, we were just looking at the 2-point correlation function, just 2 different points. Here we have 4-point correlation functions. Now, those 4 points, can they be at the same point? As you wish. If you would like to put them at the same point, fine, no problem.
Biz şimdi mesela ilk başta sayarken tüm o fiyatları identical kabul ettik yani. Fakat sonradan onların hepsine momentum assignment'tir. Bu o zaman etiketlemiş oluyoruz ve identical'lık bozulmuyor mu?
You mean before we were calling all of them to be at the same point? Now they have different momentum. Well, still they are the same fields, same particle. They are identical particles.
But they have different momentum.
So?
I can choose one of them according to their momentum.
Well, you see, you mean in calculating the symmetry factors. You see, our derivation of these rules, let's say, was from the position space. Then we had those symmetry factors. Now, if you can derive the same Feynman rules using momentum space. But you see, in that case, if you have this interaction, is actually, you can also write it in this form. Now you can define contractions in momentum space also. Although we have been always working with real position space, you can do everything in momentum space. In momentum space, the contraction of 2 fields will actually be minus I over k squared minus m squared plus I epsilon. Dirac delta k1 plus k1 minus k2 times 2 pi to the 4. So you can again do exactly the same things as we said before. Just draw your diagrams. And when you are drawing your diagrams, my vertex Well, since it's no longer really a position space, but in momentum space, this point doesn't really this vertex doesn't really correspond to a space-time point. But let me just, for the sake of demonstration, show it as a point. It's not a space point, just signifying that all the fields are coming from the same term in the Lagrangian. It has 4 lines. Each one has momenta k1, k2, k3, k4. And instead of the field at k0, x0, now you have a field with momentum, let's say k. And instead of a field at x4, x1, you have a field with momentum, let's say k prime. And now you consider all possible contractions. And you can contract this k with k1. And this propagator this time contains Dirac delta k minus k1. And you can contract k2 with k prime. That will have k2 minus k prime. And you can just contract these two. That will give you a Dirac delta k3 minus k4. And also you have the vertex factor. Now, of course, instead of contracting with k1, you can also contract with k4. You're right, they are not identical. Now, in the second case, we have Dirac delta k minus k4 instead of k minus k1. But k1, k2, k3, k4 are just dummy labels that you have chosen. Just renaming them will actually show you that you still get the same contribution. So, I mean, rather to avoid such complications, not really a complication, but such confusion, it's easier to work in the position space, derive the Feynman rules there, and then Fourier transform to momentum space. But you will essentially get the same thing. Here, still they are identical, because if you just change k1, k2, k3, k4 labels, nothing should change in your contribution. The things that you are actually fixing by choosing your matrix element is k and k prime. Other things, you just give them some names. And you are also free to change their names. So exactly the same symmetry argument will also hold here. And the symmetry factor in the Feynman diagrams, I repeat, they are not related with the labels we put there. They are just determined by just looking at the topology of the graph, of the so-called unlabeled diagram. You look at the unlabeled diagram, determine the symmetry factor, and then write the corresponding Feynman rule. And if you like, you can also label the lines afterwards. Now let us just do one more thing about these propagators. And then we can just, we will give a break. Now, you see, at the end of the day, at least in this particular example, we were calculating propagators of this form. This is in the full theory. And in the full theory, phi x will generally satisfy an equation of this form. The Lambertian minus m squared plus some potential term. Let me use it. F phi is equal to 0. And this, let us call it SF x and y. Now one can ask the question, what kind of a differential equation does this Feynman propagator satisfy? Well, since we have the phi of x over there, let's see if you do the Lambertian of x on x minus m squared plus f of phi, acting on SF of xy. You see, at first one might be tempted to say that, okay, this operator acts on phi of x, so it should give me 0. But there is one thing you should pay attention to. You see this time ordering. Time ordering of two operators is actually equal to this one. Theta x0 minus y0, phi of x, phi of y, plus theta y0 minus x0, phi of y, phi of x. Or, if you like, we can write this as theta x0 minus y0, commutator of phi of x and phi of y, plus phi of y, phi of x. What I did over here in this line is that I just used the fact that theta y0 minus x0 is actually 1 minus theta x0 minus y0, whichever one you like. You can just convert one to the other one. Now, if you act with this operator, on this time ordering thing, okay, you actually do get theta x0 minus y0. Let me just call this operator, no, let me not give it a name. X minus m squared plus f of phi acting on phi of x, phi of y. The derivative is acting on x, not on y, so I can just put it inside the commutator, plus phi of y, the same operator, acting on phi of x. So almost, remember, time ordering has these step functions. In the Lambertian we have a derivative with respect to time. Now the derivative with respect to time, I cannot just commute it with theta x0 plus minus y0. So what do I get? I get additional terms, which will be, one of them will be del 0, x0 minus y0. I have twice this term, del x0. Times del x0, the commutator, and then I have plus del x0 squared so I have additional terms if you act with the on the time ordered product with that operator. So this is 0. This is 0. Now this is not. Let me just rewrite it. Theta x minus m squared plus f of phi, acting on that time ordering, is now I have twice the Dirac delta, x0 minus y0, phi dot x, phi of y, plus Dirac delta prime, x0 minus y0, phi of x, phi of y. Now there are two things I actually need to calculate. What is the commutator of phi of x and phi of y? Well, at least the Dirac delta tells me that if x0 and y0 are different, although it is the derivative of the Dirac delta, nevertheless it will be 0. So the only thing I need to have is the equal time commutator of phi of x and phi of y. But the equal time commutator of a field with itself, well, it will just give me 0. So the second term is 0. Now the first term is not 0. Remember, what was the momentum corresponding to phi? This was the derivative of the Lagrangian density, or the derivative of the Lagrangian density with respect to phi dot, which is just phi dot. This is the momentum density corresponding my field. Now the commutator of the momentum with the field itself pi of x, phi of y, equal time commutator is actually equal to I times Dirac delta x minus y. So this operator acting on the time ordered product actually gives me, well, there's a factor 2i. There's the 2i's from the commutator over there. And then I have a Dirac delta x0 minus y0 over there. I have a three-dimensional Dirac, the remaining three-dimensional Dirac delta over there. So I have the four-dimensional Dirac delta x minus y. So this operator, no, okay. So in the free case, which is f of phi is equal to 0, del x minus m squared acting on the Feynman propagator actually gives me 2i Dirac delta to 4 x minus y. So this tells me that the Feynman propagator is actually the Green's function. Any questions? Hmm? Well, I am not so sure how we define this momentum now. The momentum commutator with phi shouldn't contain pi's. You see, we have moved pi's, all of the pi's to the momentum space operators. In position space operators, we don't have pi's. I don't like this factor 2, but it seems to be there. I mean, that 2 is just the second time derivative appearing over here. The second time derivative acting on this time ordered product would just give me the second time derivative of the second term, the first time derivative of the second term, and the first time derivative of the first term with a factor 2. It does, I mean, it doesn't matter because there is no factors of 2 in pi. So I don't know. I mean, this is what we derived at the end of. I don't know if this 2 is related with the 2 in the Lagrangian or not. I mean, for the complex case, there is no factors of 2, but still we still get that 2 over here. There are no 2's in the Lagrangian, but we have 2's over here. Any other questions? Then I have a question for you. You see, the four-dimensional Dirac delta is a Lorentz invariant. It looks the same for every observer. This operator over here is Lorentz invariant. The Feynman propagator is Lorentz invariant. And actually we had derived its expression. Well, this k squared minus m squared is Lorentz invariant. K and x is a scalar product that is Lorentz invariant. Four-dimensional momentum integral is a Lorentz invariant, so obviously it is Lorentz invariant. But on the other hand, we define this Feynman propagator using what we defined as the time-ordered product. You see, time ordering of two events or two space-time points is not necessarily Lorentz invariant. How come the right-hand side seems not Lorentz invariant, whereas the left-hand side is Lorentz invariant? That's a question for you to think about during the break or while we are smoking. Okay, see you after 10 minutes.